Okay, we're back with Chapter 4, the Bernoulli equation and pressure variation. And today we're going to describe velocity and velocity field. This is very important because this is going to lead us to describing what we mean by the Lagrangian and Eulerian approaches to describing fluid flow, fluid dynamics. And in one case, in the Lagrangian approach, we'll be specifying the velocity of a particle. We'll be following along a particle and specifying the velocity. However, in the Eulerian approach, we'll be describing the velocity field of a fluid. So let's skip through section 1 and get to section 2. We know that the definition of velocity for an object or a particle is the time derivative of the position. And so R in general here, in this case, R in general is a function of position and time. The particle can be moving around in time and in 3 dimensions. And so that's our familiar definition of velocity. And note that this is the velocity of a particle. So if we were to specify this, we'd have to be following along with the particle in x and y and z and keeping track of how its position is changing in time. The alternative approach now is to specify a velocity field. And the book does actually a nice job of this. You'll see in the book there's an equation that gets written down. The velocity vector for these two graphs on the right here are 2x, the units of that are inverse seconds, I hat minus 2y j hat. That's the equation for this velocity field. So if you look at point 1, 1, so at x, at x, y equals 1, 1, you get a velocity now of 2 meters per second. These would be in meters, as you can see in the plot here on the right. 2 meters per second in the I hat direction, in the x direction, positive x direction, and 2 meters per second in the y direction. I'm sorry. Let me just make that a j. That's the j hat direction, the y direction. So if you look at this particular point, point 1, 1, you can see that the velocity vector or the direction vector is in a positive x direction but also in a negative y direction. And that is true for any single point in this flow field. They're all kind of pointing down to positive x values and negative y values. And so if you look at these vectors in a line here, these vectors are all at x value of 0.5. You can see that they have the same x component. But as they go up in y, the y component gets larger because of this right here. 2 times y is the y component. And if you come over and look at the values at 1, you can see that they also have the same x component, but as you go up in y, they get greater and greater and greater. Same here with x equals 2, x equals 3, and x equals 4. So in each one of these cases, the x component is the same as we go across here. If we also look at y equals 4, just look at these 4 values right here, we can see that the y component for all of these is the same. So basically this equation here is being applied to this flow field. And one thing that we can do is if we look at the flow tangent, if we determine the tangential velocity along the flow, at each of these points we can draw a streamline. That's what the definition of a streamline is. And so we can see that for this particular flow field, we have this flow field specified by this, we have these streamlines. I think that's very important that you recognize that this equation can be used to draw these vectors, and these vectors, the tangential, these are pointing in a certain direction, and that tangential direction is will lead to these streamlines. This then gives you a fluid, basically a velocity field in the fluid. There are various ways of characterizing velocities of a flowing field, and I first want you to note that there's an error in the book. These are V and W values. The book has U, U, and U across here, but V is usually given, is usually the what we use for the velocity in the y direction, and W is usually the velocity in the z direction. And you can see that in Cartesian coordinates, this is a general form of the equation in the x, y, and z direction. The component of velocity in the x direction can actually be a function of x, y, z, and t, as well as the y and z directions. So this is a general expression in Cartesian coordinates, and this would be, again, important if we were following along with a fluid parcel in a flow, kind of a Lagrangian viewpoint. We'll get to that in a minute. The other way of looking at things is to, I take that back. This could be used for Lagrangian or Eulerian. This description down here can be written like this: V equals Vs of t u tangential. That's the velocity. Let me just write that a little bit nicer. That u didn't come out very well. U tangential. So this basically is showing a particle traveling along a streamline. The path is given by this blue curve here. It's probably a path line actually, but if the flow is steady, it's also a streamline. And that at any time along the path, you can see that the velocity here is given as a function of its position along the path s and time. So at any point, we can specify that as the tangential and normal, as a tangential and a normal component. And the velocity that we're interested in is the tangential component along this. We'll find that the normal component is important when we're looking at acceleration around as a fluid curves. So let's just quickly go through some key points about Lagrangian and Eulerian approaches. We'll talk about this more later, but just some key points. The basic idea, you should get this for sure. The basic idea is that the Lagrangian approach observes or describes the motion of a body of a fixed identity, that is a fluid particle. You would be following a fluid particle along as it drifts along in a fluid, like as if you were in a raft in a river, for instance, or a piece of water in a river. The Eulerian approach, on the other hand, is to observe and describe the motion of matter at spatial locations. So you would specify some points in the river to look at as the flow passes by those points. And those are two different approaches. One is following the particle, following along with the particle in the river. The other is watching the river go by it at a point. It might be as if you were just observing the river from the bank. Lagrangian dynamics is used a lot in solid mechanics. Eulerian approaches are used when things flow. In fluid mechanics tends to use the Eulerian ideas, although when we deal with controlled volumes later on in the course, you will see that we actually express the equations both in the Eulerian and Lagrangian approaches, but we set them equal to each other. So this is also important here, that the initial position in the Lagrangian approach is given, and in the Eulerian we're actually given the spatial locations of the places that we're watching the flow. It may be more simple to express the Lagrangian approach, but it tends to be harder to actually solve the problems that way. And so in a lot of cases we will use, we'll see when we deal with control volumes here, down here you can see this, we will tend to use the more complicated version because it actually ironically becomes easier to solve. The field concept is used in the Eulerian approach, and I told you a minute ago how to express the velocity field. And this is really the key point here of this, that we will be using control volumes to solve rather difficult problems in fluid mechanics. And this is a real key part of this semester, is to use the Eulerian approach to solve problems of both mass, momentum, and energy. And I believe that's it. If you want, you can look at the video called Eulerian and Lagrangian Description at the MIT website. Okay, thanks.